Okay, so we're going to continue to look at fast search operations. There's actually a really nice way to look for strings or for anything that is based off of a set of symbols very, very quickly at the cost of using a lot more memory than balanced search trees. And this technique, which I'll actually show some refinements of as well, but the basic technique is called a trie, T-R-I-E. It comes from the word retrieval. I think it was originally supposed to be pronounced a tree, but nobody does because it's too confusing. And the idea is that we can search, I'll say strings, but anything that's based off of a dictionary of characters in order n operations, where n is now the length of the character string. Okay, so the nice thing is that for a particular length string, that gives us constant time lookup. Okay, so for a string of length 10, it's just going to be order 10 operations to find it, independent of what it is, right? So that's going to be guaranteed. And it's going to come at the cost of a lot of memory, so I'm going to show you a more compact representation of it next. But I want to show you the basic idea. It's actually quite simple, and it's a little hard to draw, so I'll try to draw it, and then after I fail, but I think I convey the main point, I'll go back to our drawing program, and I'll see if we can't draw it a little bit better there. So let me just get rid of this, and let me tell you the basic idea. We need a dictionary. So normally the dictionary, say if we're doing strings, would just be all the, say, letters in the English alphabet. It'd be 26 characters if we just did lowercase and no special symbols. But that would be totally impossible to draw. I'll show you the code, and it looks the same in the code. But for the purposes of trying to draw something, let's say our dictionary is just 4 letters. Okay. And so our dictionary will basically say A, E, some letters that are easy to make words out of. And let's just imagine that, which is the case, we associate an integer index with each of these, because the idea is that we want to be able to index directly into an array in order to represent one of them. Okay, so if we imagine some node which represents a character, it's going to have, for this dictionary, 4 children, and the 4 children are child 0, child 1, child 2, and child 3. Child 0 is A, child 1 is E, child 2 is P, child 3 is T. And the idea is therefore that we can represent a child node of any of the letters simply by going directly to that child and changing it from null to not null. Okay, and therefore you assume there's some associative array or some simple translation between the character and an integer, which is always the case. Okay, so it's easy. So what does this look like then? Well, we want to start putting words in the data structure. And we usually start with, one way to do this is just to think that, well, there's this sort of dummy root node, which is above all the other nodes. And every single node in the trie is going to represent a character, and it's going to have 4 children, where 4 is the number of elements in the dictionary here, maybe 26 if you were doing the whole English alphabet. So that's going to be expensive. You don't obviously have to allocate the memory for each one, but let's just imagine that we just have an array of 4 children just for simplicity, and try to spread it out a little bit. Okay, so those 4 children, let's say they start off as null, null. And then when I start adding things to the trie, I'll ask if they're null, and if they are, I will make them represent one of the character, whatever the corresponding character is. Okay, so let's take a word, for example. We'll add the word, let's see, pet. Or let's say tap. We'll start with tap, it's easier. Okay, so to add the word tap, we're going to say, let's go to, what did I say? Sorry. Yeah, tap. Let's go to, I picked one that's going to be a little hard to draw. So let me just move this over a little bit, buy myself a little bit more room. Okay, so let's slide this over here since I'm going to be working on the right side of the tree. And I then say, okay, I'll start at the root, and then I say, okay, it is the third subchild of root allocated. It's null right now, so I'm going to have to create a node, and I'm going to have to say the node does not represent an end of word. This is usually just a field that we carry around, marking the ends of words as we traverse this tree. And so I'll have a little symbol that says that the end of word is an end of word marking, but T does not represent a word. So I've really just malloc the node here, and I've created its children. That's the key. Okay. And I've set each of them equal to null. So I'll just say for null. And then I say, okay, now I want the 0th child of the T node. Does it exist? No, it's null. Okay, so what I want to do is I want to allocate it. And when I allocate it, I have to allocate its 4 children. I'm going to run out of room fast, but you get the idea. And then each of these is null. Okay. And then I want to, I said tap, so I immediately know it's the 2nd child of the node A. And I can add it. And then that represents a word. So I'm going to set this bit inside the structure, whatever this integer field, to have an end of word marker. So I know that I've passed a word as I'm traversing it, right? So I will see not only the word that I'm going to find as I traverse this tree, but all of the subwords that make up that word. So this is an excellent technique for doing substring things, for doing autocomplete, right? This is the way it's normally done. So I'm done with tap, and notice if I want to find tap, I simply traverse the tree, indexing directly to the children, and ask if the 3rd node exists, if its 0th node exists, and if its 2nd node exists. And if it does, then I have found tap, and that's what I want to do. I want to find something fast, and that's always going to be just 3 operations. So I could add, let me think, something a little like apt, something over here to the left. So if I add apt, it will look exactly the same. Right, I'm just going to malloc a node. I'm going to give it 4 children. I'm going to immediately index into the 3rd child. So let me get rid of that. I'm going to, then it will have 4 children and so forth, right? So in this case, I'll do it right now. And then I mark that that's the end of a word. Okay, so this is a very clever way to build a dictionary that uses a lot of memory, but and I'm going to improve upon it a little bit, but I think the basic idea is very clever and very efficient. So say I want to do tape. Okay, well, tape, I say T exists, A exists, P exists. I never created the children here, and the children are going to be null, except I won't, well, I'll just do it and then erase it for effect. Okay, then I'm going to say, okay, I've got to add the E. That's okay. I add its children, and I mark that that's the end of a word. Okay. So if we're willing to spend the memory, we can build, and if we have lots of words, such as in our dictionary, that are substrings of other words, it can be more efficient. And if we don't, then it will be less efficient. It will always work, but we're always just going to go however many levels of the tree we have characters in order to add or define the word that we want. So this is a little bit of a rough depiction. What I want to do is show you first an animation that's a little cleaner, that spaces things better. And then I'll show you a little bit of code. And then I will, in the next set of lectures, refine the idea and consider how we can do some better memory savings. Okay, but this is, I think, a very clever and potentially useful data structure.